Hello and welcome. In this video, we're going to be talking about periodic trends and specifically the trends of atomic radius, ionization energy, electron affinity, ionic radius, and electronegativity. And while there are other trends, those will be covered possibly in a future video. But right now, these are the main ones that you're going to need to know for whether you're in general chemistry, pre-AP chemistry, or AP chemistry. These are the main 5 trends that are focused on in those courses. When you go off to college, you will look at some other ones, but we're going to focus on these for this video. So let's go on and jump directly into it. So in this, periodic trends for the periodic table, the first thing you need to know is that there are period trends and then there are group trends. In period trends, these are the trends that go across the period. Typically, we look at them from left to right, and of course, they're called period trends because they're across a period. Then there are trends within the families or within the columns of the periodic table, and these are referred to as either group trends or family trends. Now, before I go on into the first trend that we're going to talk about, atomic radius, I do want to mention that I've done a previous video, periodic trends and introduction, where I talk about Coulomb's law, I talk about effective nuclear charge, and I talk about electron shielding. If you have not seen that video, I recommend you stop this video, go back and watch that other one first, because I'm going to be using a lot of those terms and those concepts as we go through these 5 periodic trends. If you've already seen that video, then we're ready to go. So the first trend that we're talking about is atomic radius. And this is the number 1 trend in all of the trends. The reason being, all the other trends are based on atomic radius. Because as we look at atomic radius, and we see how that radius changes, looking at Coulomb's law, we calculate a new force of attraction between the nucleus and those electrons. And that attractive force, as measured or talked about in terms of effective nuclear charge, is how we then explain the other trends. So atomic radius, this by definition is the total distance from an atom's nucleus, the center of that nucleus, to the outermost orbital of an electron. So when we talk about an atom, we do have to recognize that the predominant model that is used in high school is that of the Bohr model, or the planetary model of the atom, where you've got the nucleus and then you've got these rings of electrons like they're in orbit around that nucleus. Now in college and in your advanced chemistry, AP chemistry, pre-AP chemistry, you will talk about the quantum mechanical model. But even the quantum mechanical model simplifies down, and we typically talk about it in terms of the Bohr model. So in this, when we see that outermost orbital, it's also okay to talk about it as that outermost ring of electrons. Okay, so when we find this, the only way to find that radius is to actually take 2 atoms of the same type, bring them into proximity until they start to repel each other. And then we measure the distance from nucleus to nucleus, and then we divide that distance in half. Furthermore, we measure this in terms of nanometers, or nm. Okay, so just to keep that in mind, also want to mention that you will see charts every once in a while that do atomic radius in terms of picometers, as well as ionic radius, which is a trend we'll get to in a little bit, done in picometers. But nanometers is kind of the standard measurement that we use. So when we talk about these trends, I'm going to talk about the period trend first and then the group trend. So when we talk about atomic radii, the period trend is that as you go across, left to right across that period, because we've got greater Coulombic forces, because we're increasing our number of protons and our number of electrons, so Q1 and Q2 are increasing, force of attraction increases. And because that force of attraction increases, we see a greater pull on the electrons, and therefore radius decreases as you go across. As far as group trend, we find that as we go down a column, we're going to end up getting a larger and larger, get tongue-tied there. We're going to get a larger and larger radius because we're adding on these energy levels. Okay? We're adding additional orbitals. So as a result, we're going to automatically see an increase in radius, but also we see an increase in radius because as we add those levels, our effective nuclear charge is decreased because of increased shielding. So the net effect is that the nucleus ends up having less pull on those electrons, and as a result, those electrons can drift further outwards. So one of the ways that I was shown to kind of remember this idea of atomic radius as you go across, as I move my keyboard out of the way, is to think about a snowman. So if I draw a snowman up here in the corner, this is the idea of my radius as I go down a column. And then as you go across the period, take that snowman and just push them over. And what you get is the decrease as you go across. So that's probably the easiest way to remember the period trend and the group trend for atomic radius, is just think about it as being a snowman. Okay? Largest radius at the bottom, decreasing as you go up, or smallest radius at the top, increases as you go downward. And then if you push that snowman over, then as you go across, radius gets smaller and smaller. So hopefully that's a helpful little trick for you to remember atomic radius. And again, the reason why atomic radius is the most important is that as we start looking at other trends, we're going to constantly go back to the idea of the atomic radius and how that radius affects the effective nuclear charge, as well as the shielding effect. Okay? So here's a nice little depiction of atomic radius trends. And again, you can see as you move down a column, that radius increases. As you move across, radius decreases. Now, I do want to mention real quick, this is a general trend. Okay? It's not a consistent decrease as you go across. There are fluctuations in it. Typically, we see those fluctuations partway through the non-metals. Okay, when you get to around carbon or your half-filled sublevels, we see some changes that are going on in that radius. Okay, so if I'm looking through this, by the time that I hit nitrogen right here, I actually see a slight increase in the same thing as I'm going across each subsequent period. Okay, and later video, I'll get into why that occurs. Okay, but general trend as you go across. So the next trend is ionization energy, and a couple of definitions before we get into the actual trend of ionization energy. So the first definition that you need to know is what exactly is an ion. And this is nothing more than a charged particle, and you get this charged particle by either gaining or losing an electron or electrons. Now, if you have something called a cation, these are positively charged particles or atoms because you've lost an electron or electrons. And typically you're going to see these as your metals like sodium, lithium, potassium, rubidium, magnesium, calcium, etc. And the amount of positive charge tells you how many electrons were lost. Right? But those are cations. Then you have anions. And these are negatively charged particles or atoms because you've gained electrons. These are typically going to be your nonmetals: nitrogen, oxygen, fluorine, chlorine, bromine, things of that nature. And again, the numerical value of that charge tells you how many electrons were gained. So if I'm looking at something, for example, like Ca2 positive, that positive tells me that I've lost electrons. The 2 tells me how many electrons were lost. Likewise, if I'm looking at something like O2 negative, the negative tells me that I've gained electrons, and that value of 2 tells me how many electrons have been gained. Okay? So, cation, anion. Also, an easy way to remember which one is which, when you think about cation, when you write this out, think about that T as being a positive sign. So right there, Ca positive ion. So cation is your positive ion, which by default would make the anion your negative ion. Okay? So that's first three terms that you need to be familiar with. Other two terms, ionization. This is the actual process of creating those ions by gaining or losing electrons. And then the energy required to ionize something, that is ionization energy. And that's the trend that we're about to take a look at. But by strict definition, ionization energy, also abbreviated as IE, this is the energy required to remove just one electron from a neutral atom, and we measure this in terms of kilojoules per mole. So ionization energy is the energy required to remove one electron from a neutral atom, but because that's typically such a small amount, we look at actually removing 1 mole of electrons from 1 mole of atoms, and hence why we measure this in kilojoules per mole. Okay? Not just a single atom, but each individual atom, okay? Or moles of atoms, rather. So here's the actual trend now. Again, period trend and then group trend. So for ionization energy, the period trend is that as you go across the periodic table, ionization energy is going to increase. The reason it increases is because radius decreases. If we go back to Coulomb's law, as radius decreases, remember, force of attraction is going to increase. And because that force of attraction increases, it becomes more and more difficult to remove that electron from the atom. And the more difficult it is to remove the electron, the more energy it's going to take. So as radius decreases, ionization energy increases. And again, as you'll see in textbooks, it says it's due to greater Coulombic forces or increased ZEF. In other words, the nucleus has a greater pull, and therefore it requires more energy to remove. So looking at the period trend, we can probably guess what that group trend is going to be. Because if we go back to atomic radius, if down a column or down a group, radius is increasing, if you go back to Coulomb's law, as radius increases, force of attraction decreases. And because that force of attraction decreases, this means ionization energy generally is going to decrease as you move down that group, because we've got lesser Coulombic forces, lesser ZEF or weaker ZEF. The electrons are further away from the nucleus, so there's more shielding, which means, again, that effective nuclear charge, that attractive force for those outermost electrons to the nucleus is lessened, it's weaker, and as a result, it's easier to remove those electrons. So as radius increases, ionization energy is going to decrease. So that's ionization energy. Here's two depictions that you can see of this typically in textbooks. The first one is the periodic table that just labels and shows you as you go across the period, ionization energy increases, move downwards, ionization energy decreases. The other one, this one down here that I'm circling with my cursor, shows you kind of the relationship from period to period, as well as those columns. So you can see hydrogen, and then it increases to helium because of a smaller radius. And then an energy level, larger radius, less energy required to move the electron. And then as we move across the periodic table and radius decreases, we see a general increasing of ionization energy till I hit column 18, the noble gases, smallest radius for that period, so highest ionization energy. Then I go to period 3, at another energy level, and again we see energy drop. Okay? And then we can go across. Then we get to the D sublevel, which is kind of wonky in there, but again, a general increase as you go across. And then we hit our non-metals, and then period 4, etc. So a general increase again as you go across, and a general decrease as you move down. So notice helium, neon, argon, krypton, xenon, radon, all in the same period. And as I go down that period, I see a general decrease. So this is two different ways that you can see ionization energy represented. Okay, so that's ionization energy. The other concept that you need to know for ionization energy is that the tables that I've just shown you are for the first ionization energy. But if I want to remove more than one electron, so I go back to that idea of calcium being 2 positive, I've removed 2 electrons, which means there was an ionization energy for the first of those 2 electrons, and then a second ionization energy to remove that second electron. And the second ionization energy is typically larger because I'm going to increase Coulombic forces. Okay? So in this table that I'm showing you here, once you remove the first electron, say for sodium, okay, now I'm moving to an inner shell electron, one that is closer in, and I see a huge increase in energy. So a lot of times what you'll see in the advanced chemistries, AP chemistry, pre-AP chemistry, is that they will give you a table like this, and they don't tell you what the element is, and they ask you for this element, determine what period it would be in. So what you can do, or not what period, sorry, which family it would be in. So you can work backwards and say, all right, so this is the innermost, and it was the first, second, third, fourth electron to be removed. So I can work backwards and find that it would be in the family that includes aluminum. Okay, so successive ionization energies as you go through. But here's what I want you to notice. These highest ionization energies is always when you're trying to remove an electron from an element that has what's called the noble gas configuration. In other words, it has the same electron arrangement as what you'd find in a noble gas. And noble gases are extremely stable. So as a result, they don't want to lose electrons. So you see this peak in ionization energies. Okay. But enough on ionization energy. The next one is electron affinity. And electron affinity is the energy change that results from adding an electron to a neutral gaseous atom. So ionization energy is removing that electron. Electron affinity is trying to add one in. And what we find is that when we add in the electron, if that change is negative, then we release energy. And that's very easy to do. So we typically find negative values associated with things that want to have these electrons added into them. Positive change, energy has been invested into the atom, which means it's hard to do. Okay, so these are things that don't want to gain electrons. And we again measure electron affinity in terms of kilojoules per mole. So let's look at period and group trend. So period trend, as I go across, electron affinity increases as you go across due to greater Coulombic forces. In other words, there's increased attractive forces, and that nucleus has a greater pull. Because there's a greater pull for that electron, it's easier to put that electron in, and it releases energy in doing so. Conversely, a group trend, again, that radius is getting larger. It's already having a difficult time trying to keep the electrons that it currently has. It doesn't really want to gain another one. So as a result, in general, electron affinity decreases or becomes more difficult as you go down a group. Okay? And again, this is because of increased atomic radii and increased electron repulsive forces. I've got this large radius, and adding in an electron is going to increase those repulsive forces and push that radius even further out. That nucleus is going to have an extremely difficult time trying to keep that electron in place. So as a result, it's very difficult to add an electron to a large radius. So this is why we see the period trend and the group trends that we do. So on the periodic table, again, as you go across, electron affinity increases, electron affinity decreases as you move down a column. This also has a role in why we find that our metals tend to lose electrons and nonmetals tend to gain. High electron affinity, these want to gain, these don't. Okay? And that goes back towards electron configuration of a noble gas. So that's electron affinity. Next one, ionic radius. So ionic radius, by definition, is the measure of an atom's ion in a crystal lattice. So just like I talked about for atomic radius, we take two atoms that are similar and we push them together so they start to repel, and we measure from nucleus to nucleus. ionic radius, we have to have some type of crystalline lattice structure. Okay, and then what we do is we measure the distance between those two ions that are bonded together, ionically bonded, and we half that distance between those two ions when they're barely touching each other. So we try to force them together and then measure that distance and divide it in half. That's our ionic radius. As far as trends, going back to this idea of cations, these are your positive ions. They've lost electrons. And because you've lost electrons, we again increase that effective nuclear charge. Okay, if I start out with, say, a Q1 and Q2 of certain values, and then I remove that that electron, then what ends up happening is my Coulombic forces increase, because as I remove that electron, my effective nuclear charge, my number of protons that's still the same, now attracting fewer electrons. In essence, that attractive force is divided unequally between them. For example, if I had 2 protons, 2 electrons, then each proton attracts 1 electron. Well, if I remove an electron, now I've got 2 protons attracting 1 electron. That's a much greater attractive force. So Coulombic forces, or ZEF, increases, and it pulls that electron cloud inward. For anions, because I'm adding electrons in, we see the reverse. Okay? As I add in an electron, repulsive forces increase. So now instead of 2 protons, 2 electrons in that attractive force being split evenly, I add an electron, and now those 2 protons have to split their attractive force amongst 3 electrons. They can't hold as tightly, and we see that atomic radius increase because these 3 electrons are repelling each other outwards. So for anions, you get increased atomic radius due to greater electron repulsion and no increase in that ZEF. Okay? So this is cations and anions. Notice this is not a period trend or a group trend, because cations and anions, we first have to compare the ion to the neutral atom. Then, once we get the idea that cations, when I get a neutral atom that loses an electron and its radius decreases, then I can start comparing ions to ions within that group. For anions, as they gain electrons and their radius increases, now that I know that nonmetal anions are all going to increase compared to their neutral atom, now I can compare within that group or that period. So first, cations and anions and what happens for the ion versus the neutral. And now we can look at period and group trend. So for the period trend, ionic radius decreases until group 15, because at group 15, that's where we start seeing atoms start to gain electrons. So ionic radius is going to decrease because I'm dealing with cations. Group 15, I'm now switched to dealing with anions, and that radius suddenly increases. But then as I go on across groups 15, 16, and 17, it decreases again. So what you get for the period trend is this decrease through your nonmetals, and then at group 15, when we hit, a decrease through your metals that are forming cations, and then at group 15, a sudden increase in radius, because now I'm dealing with nonmetals that gained electrons, and then a decrease again. For group trend, all the way down, we see ionic radius increasing because you've got greater energy level of electrons. So let's take a look at a chart. So this is the way it looks. The ions are the red and the blue. Okay? The parent atoms, or the neutral atoms, are the brown. So you can see here we are with the metals that compared, the ion compared to the neutral, each ion has a decreased radius. So as I go across, radius decreases. As I move downwards, radius increases. When I look at my nonmetals that gain electrons, become anions, again, we see their radius increase when I compare neutral versus ion. But as I go across ion to ion, I still see a decrease in radius, but an increase as I move downwards. So as a result, the group and period trends are the same as what they are for atomic radius. Okay? Where most students get caught up is the fact that the trend is continuous. Again, you see this decrease through the metals, a sudden increase, and then a decrease through those non-metals. Okay, so that's ionic radius. Then lastly, we have electronegativity. And electronegativity is the tendency of an atom participating in a covalent bond, in other words, a sharing of electrons, to attract bonding electrons. So the idea here is you've got two atoms that are bonded covalently by sharing an electron, but one atom is going to have a stronger pull for the electrons in that bond than the other. And that's measured by electronegativity. So this oftentimes is thought of as the desire to acquire electrons from another atom. This goes into what type of covalent bond is formed. Is it purely covalent where they both have the same electronegativity and an equal pull, or does one have a larger electronegativity, pulls the electrons over towards it, and you get what's called a polar bond? So electronegativity has implications when you get to types of bonds. But as far as trends, period trend, as you go across, we see electronegativity increase. And again, the reason we see electronegativity increase is that radius is decreasing. As radius decreases, Coulombic forces increase, our Zeph increases. Because of that, the nucleus has a greater pull on the electrons, whether they are pulling them from an outside source or they're pulling them towards them within a bond. As far as the group trend, you can probably already guess it. Because radius is increasing, electronegativity is going to decrease. Because again, as that radius increases, Coulombic forces decrease, my Zeph decreases, electron shielding increases, the nucleus has less of a pull on the electrons that are already there. It's not going to be able to pull in additional electrons through a bond. So electronegativity decreases as you move down a period or down a column. Okay, so this is again an overview, periodic trend. As you move down, electronegativity decreases. As you go across, it increases. And as a summary for 3 out of these 5, here's what I want you to notice. Atomic radius decreases as you go across. Ionization energy, electronegativity, and electron affinity, they all increase. Ionic radius also decreases. So here's the key to understanding all this. As you go across a period, your radius, whether it's atomic or ionic, decreases, and your other trends all increase. Conversely, as I move down a column, notice atomic radius increases, but my other trends, they all decrease. So as you're looking down a column or down a family, down a group, your radius, again, regardless of whether it's atomic or ionic, that radius increases. And as a result, all your other trends, ionization energy, electronegativity, electron affinity, they are all going to decrease. So as long as you know the trend for radius, then you know that the other ones are opposite. The only thing that's left is the reason why they're opposite. And again, that goes back to Coulomb's law, effective nuclear charge, and electron shielding. So hopefully all this has made sense. If not, feel free to leave questions in the comments and I'll get back to you as soon as possible. Also, if you've got ideas for future videos, leave those in the comments as well. Okay. Thanks. Take care.